Welcome, guys, to the part 2 of buoyancy and flotation lecture. Today we are going to discuss something about the center of buoyancy, that is for submerged and for floating bodies. Let us just start with the general. If different geometries are there, say like if it's a cube, if it's a triangle, the center of gravity, if the body is just outside of the fluid, it's in the in this video we are marking G as center of gravity, right? And if this same body is inside the fluid, say like this, this is the fluid, and particularly a static fluid, then this is the volume of liquid displaced by the fluid, and the center of buoyancy, B, will be the center of gravity of this displaced fluid. So I am considering this is the center of buoyancy. So why we are studying this part again, I'll see something called as the effect of disturbance. What is the effect of disturbance? Say in a submerged body case, if there was a body inside the fluid, and if this was the central axis of the fluid, and if I gave it a slight nudge from the right hand side, then it would bend, it would tilt like this, right? It would tilt like this. If we see the center of gravity, so center of gravity was here only, and if the overall body was a uniform body, then center of gravity and center of buoyancy would be at the same position, right? And once we gave the disturbance, the overall volume of the body did not change, which means what? Which means that the buoyant center and the center of gravity are at the same place, right? So it didn't change. So we can write it here like, since the shape of displaced volume remains same during disturbance, so center of buoyancy remains at the same position on the vertical axis of the body, right? If we go for the floating body case, if you want to know what is floating body and what is submerged body, you can go to my previous lecture, part 1. However, now we are considering a floating body. Say this is a floating body, right? And if we give it, this is the central axis of the body, this is G, and as we know that it is not fully inside the water, means this is the water displaced by the body, and center of buoyancy will be the center of gravity of this water. So center of buoyancy is somewhat below, right? Then if we give a notch here and disturb the body, then the body will tilt like this, right? right? I have changed the shape of the body. It should not change actually. So it will be like this. The axial line will be tilted enough, and we can see that now the liquid displaced by the body has changed. It has taken a shape of something, which means what? The center of gravity of the body remains same. However, the center of gravity of the displaced fluid has now changed, and it will shift in the right direction. Maybe here, maybe here, maybe here. It can be anywhere. So depending upon where the depending upon the where the where the center of buoyancy is, you can see that the in the previous case, the center of buoyancy was not changing. However, in case of a floating body, the center of buoyancy is trying to shift in the right direction. So we can write, since the shape of displaced volume changes, right, during disturbance. So center of buoyancy changes its location and shifts from the vertical axis of the body. It has left the vertical axis. Initially, both center of gravity and buoyancy was on the same vertical axis. Here in the submerged body case, they are on the same vertical axis. However, in the floating body case, the center of buoyancy has shifted from the vertical axis of the body. Okay, now we can move to the stability part. So in class 11th in physics we have already studied stability. I'll try to make a analogy, and we need to study the stability of submerged as well as floating bodies. So we need to be very clear on what is stability. So you can recall these diagrams of a bowl and a ball, right? So in the first part, if I give a disturbance to the ball and it comes like here, then there is a force. We know that there is always weight acting on the body, and there will be a component of the force, that is mg some sine theta, that will try to make the body come to its neutral position again, which is called as the restoring force. And whenever it comes to the initial position or the mean position again, then it was called as stable equilibrium, if you can remember. Similarly, if the ball was on this ball and we tried to push it here, there was no restoring force on this ball, so it was not coming in its initial neutral position. This was the initial neutral position for each of the balls. So this is unstable equilibrium, and this is neutral equilibrium. If you try to move the ball from here to here, it will come here and stop. So this is a neutral equilibrium. So this is as far as what we have learned in the 11th standard. However, we need to apply this in the stability of submerged as well as floating bodies. So what we'll do, we'll first study the stability of submerged bodies. As we know, the submerged bodies are easier to deal with, and okay, let's see how they are easier. So I'll again take three scenarios of body inside water. So let us take a body, say this is the body. Okay, see, this is the body, and this is the central axis of the body. And imagine there is a weight on this body in the top portion. So if the weight hadn't been there, then center of gravity would have been here. However, if the here, and since the weight is there, it will shift upward, right? So center of gravity of the body will be somewhere here, and the weight displaced by the body is the volume of the weight displaced by the body, weight of the fluid displaced by the body is this rectangle. So it will be, the buoyant center will be somewhere in here. If I try to give, if I try to rotate this body, okay, if I try to rotate this body like this, okay, you can see that since the body is submerged, the overall positions of center of gravity and buoyant center will not change. And what is the utility of center of gravity and buoyant center is, from center of gravity the weight of the body passes, the force, and from center of buoyancy what passes, the buoyant force passes. As we can see that this particular arrangement is creating what, a couple in the clockwise direction, which is not maintaining the initial position was this. It will try to turn the body in an upside down manner. So this will be an unstable equilibrium. Okay, similarly let us do the second case. See now I have a body, okay, this is the central axis of the body, and now the weight part is in the bottom of the body. So now the center of gravity is below, and buoyant center, as we know that it is the weight of the liquid displaced, and the buoyant center will be on the center of gravity of the liquid displaced by the body. Again we'll do the same thing, we'll try to give the body a disturbance, and I'll see what happens. So we have given a disturbance to the body, okay. Again we'll draw the forces acting on the body. We'll draw the forces acting on the body. So from center of gravity mg is acting, and from buoyant center force of buoyancy is acting. And now you can see this particular force arrangement is making a couple in the anti-clockwise direction, which is trying to regain this initial shape, right? But in the previous it was not like that. So this is a stable equilibrium. I'm not writing it as such, okay, as you guys can understand. Now let us just take a normal body without any weights in the top or bottom. So as we know, let us draw. The center of gravity will be at the middle, since there is no there are no weights associated. Now again I'll try to give this part a tilt. So let us give this a tilt, or I disturb this part. Center of gravity and buoyant center position will not change, which means what which means that the force of gravity, that is mass of body, into G, and force of buoyancy Fb will be acting on the same point, and it will not create any couple. If it does not create any couple, means that the body after disturbance will remain at the same position, which is what we studied in the neutral equilibrium case. Okay, now let us move to the stability of the floating bodies. So floating bodies are a little complicated, and we need to give particular attention to this. So let us just say stability of floating bodies, because the position of buoyant center will change after disturbance. So let us again take 3 scenarios, maybe a little down. 3 scenarios, 1, 2, 3. So first body is floating here. Okay, this is the central line, this is the center of gravity, this is the center of buoyancy. Okay, and I need to tilt it, so I'll select it. Let us tilt it. So now this is the tilting part. Okay, we can now easily see that the tilting has made the the displaced fluid part, means this part. I'll draw it again. This part change, which means what? Means that the center of buoyancy will be somewhere here, and this center of buoyancy might cross this center of gravity point in the vertical line. So let us assume that this vertical line has been crossed by the center of buoyancy line. So now after disturbance we give the force. So this is mg, mbg, and force of buoyancy will be like this, fb. Here another term comes out, which is the metacenter. And metacenter is what? Metacenter is the point of intersection of vertical line passing through the new center of buoyancy. So new center of buoyancy was, say, b1 here, say b1 here. So it is the point of intersection. So the one more point, that is m, which is the metacenter, will come here, and metacenter is there only in case of floating bodies. So we can see that this particular arrangement is creating a couple like this, which is trying to regain its shape. So this will be what? This will be stable equilibrium. Let us move to the other part. Say this is the body. This is the central axis of the body. Center of gravity is somewhere here. Initial center of buoyancy is somewhere here. Okay. Now I give a tilt. A disturbance to the body. Let us give a disturbance to the body. So once I give the disturbance, it will rotate like this. Okay. Now let us assume that the center of gravity, the center of buoyancy, the new center of buoyancy does not cross this line. So it is somewhere here. Okay. Now if we draw the forces on the body, say B1 is here, B1, the new center of buoyancy. So mg, mbg, which is the weight of the body, and from new center of buoyancy there will be a buoyant force passing, and the intersection of the vertical line, buoyant force and the vertical axis is called as the metacenter. So metacenter is in between center of gravity and, so this M is called the metacenter. Now we can see that this particular arrangement is creating a couple in the clockwise direction, which is what, which is trying to rotate the body somewhere not in the initial position but upside down. So that will create a unstable equilibrium. Now moving towards the neutral equilibrium part, let's just say, okay, let's just say we have this body again. I could have just copied it. We have this body again here. Now I'm giving it a disturbance like this, and now once the disturbance is given, say now the new buoyant center lies exactly below the center of gravity. So what will happen in this case is that once we draw the weight of the body through the center of gravity and buoyant force from the new center of buoyancy, we'll see that the metacenter was what? Metacenter was again the point of intersection of the buoyant force and the vertical axis. This is the vertical axis. So I am repeating it again. So point of intersection here will be at the center of gravity of the body only. This is the metacenter. So metacenter definition is important. It is generally mostly asked in the exam, so that's why I am explaining in details. We can see that there is no couple generated, and since there is no couple generated, there will be no rotational motion of this body. Hence, this is a neutral equilibrium case. So we are done with the stability of floating bodies and stability of submerged bodies. Now we can easily define what is metacenter. So metacenter, as I've already said, that metacenter M. So metacenter M is what? It is defined as the point of intersection of vertical line. Vertical line passing through the new center of buoyancy, which means the line of action of buoyant force, and vertical axis of the body and the very small angular tilt of the body. Another definition can be it is a point about which body is oscillating. This is the point about which the body will oscillating under very small angular tilt given to the body. Now we should always know that the metacentric height, something related to metacenter, is the metacentric height. What? Metacentric height. What is metacentric height? It is the distance between G and M, means center of gravity of the body and metacenter. It can be positive, it can be negative, and it can be 0. Positive is when M is when M is below positive when m is above g, m is below g, and 0 is when m is on g. Okay, so metacentric height, there is a deduction of formula for calculating the metacentric height, that is gm, and there is an experimental theoretical formula, deduction, which I would like you to see it from R.K. Bansal, how it is derived. I will just write the formula and I will show you how to use the formula. So it is metacentric height gm is equal to moment of inertia divided by volume of displaced fluid but minus b into g, means distance between the center of buoyancy and center of gravity. Again I'll write the same thing. gm is positive, means gm is greater than 0, then it is a stable equilibrium case. gm is less than 0, then it is an unstable equilibrium case. And gm is equal to 0, that means that it is a neutral equilibrium case. This I, that is the moment of inertia, we have to be very careful in writing this moment of inertia. So moment of inertia, I'll show you where you should take this moment of inertia. So moment of inertia of plane, cut, this is important, cut by free surface level of what? Of liquid. So if let's just say if I want to apply, suppose, let us remember, say like if inside the water, again this is for a metacentric height case. So okay, say like a cylinder is floating on the, so I should take here moment of inertia, I should take here, this is the moment of inertia. So if this is r, the radius, then moment of inertia of this disc, this is what? This is a particular disc. So moment of inertia for this particular disc will be pi r to the power 4 divided by 4. Okay, again if I want to calculate the g will be somewhere here. G will be how much? If this height is what? h, so g height will be what? h2, h by 2, right? Buoyant center will be somewhere here, since the liquid displaced by the body is this much. So buoyant center will be below the, if the submerged height, if the floating height of the body is small h, then the buoyant center will be the here, and this distance will be small h by 2. Okay, similarly if instead of a cylinder they have given you a cone, how will you tackle the problem? So let us see that. Okay, I have a cone. So which eye you should take? Say the cone base radius is r, so you cannot take the moment of inertia of this portion, you have to take the cutted portion, moment of inertia of plane by free surface level of the liquid, means this part, this particular circle. So for that you need to calculate this small r, and once you calculate this small r, then you can calculate the moment of inertia of this plate as I is equal to pi small r to the power 4 divided by 4. Okay, then what do we need? We need volume displaced. For volume we need the dimensions of the body. So if the initial height of the cone was h, then center of gravity will be somewhere here, and center of gravity height will be how much? For cone it is 3 by 4h, and center of buoyancy will be below because the liquid displaced by the cone is not equal to the volume of the cone. So B, if the total submergence height or depth is small h, then this will be how much? This will be again 3 by 4 of small h. Then again we'll do the questions and we'll know what to calculate and how to calculate. This is for general understanding. Next we are up for a question on metacentric height. So this is the question we are going to solve as in metacentric height. For the metacentric height, I need you to understanding the concept of metacentric height, you need to solve at least 2 to 3 different types of problem. I'm going to show you one, and the rest is for you guys to explore. So let us just say that they have given a wooden cylinder. Okay, wooden cylinder, specific gravity which knows it's lighter than water. Circular cross section is required to float in oil. Okay, so find the L by D ratio for the cylinder to float with its longitudinal axis vertical in the oil. Okay, so they have not asked anywhere that it's a metacentric height question, but it is a metacentric height question. So they have said that okay, there is a cylinder. So I will write density of the cylinder is, if the specific gravity is 0.6, the density will be 0.6 into 1000, right? So it will be around 600, and the oil in which it is floating, density of that oil is what? Density of that oil is, again, oil specific gravity is given 0.9 specific gravity into density of water, that is 900, which means 900 kg per meter cube, and this is 600 kg per meter cube. Okay, that is okay. Then they have not given any dimension, so we want to calculate the dimension. Let us just say okay, this is, they have said that this is D and this is what? This is L. I know that there is a central line and the cylinder is, we want to find the L by D ratio when the cylinder is floating with its longitudinal axis. This is the longitudinal axis in vertical, this is vertical. Okay, so there will be a center of gravity. Let me mark it with black. There will be a center of buoyancy. Since it is floating, since the wooden block is wooden cylinder, again block, it is not a block now. So wooden cylinder is floating, which means what? The weight of the body means the weight of the cylinder will be balanced by what? Will be balanced by the force of buoyancy on the cylinder, and force of buoyancy is what? Weight of liquid displaced. Liquid is what? Oil displaced by the cylinder. So this is, so weight of cylinder is what? Weight of cylinder is mass into volume of the cylinder. Mass is again, I'll write mass of the body, mass of the cylinder into G, and weight of the liquid will be what? We know that force of buoyancy is what? Weight of the liquid displaced means oil into G into volume of the liquid displaced. For calculating the volume of the liquid displaced, we need to consider one more thing here in the diagram, which is the depth of submergence. Means how much depth let, I will say, because I am considering say h height is inside the oil. So buoyant center will be somewhere from h by 2, right? Let us give this point a name A. So AB is how much? AB is h by 2. What is AG? AG is how much? Capital L by 2, isn't it? So let us first solve this equation that I have in the right side. So mass is what? Density into volume of the cylinder. Volume of the cylinder is what? Volume of the cylinder is volume of the base. So volume of the base is pi by 4 d square into L. This is the volume into G. Volume of the liquid displaced will be what? Pi by 4 d square, and it will go till only this part. So it will be small h. So G is cancelled. Pi d square is cancelled. So we can get an h value, which is what is the density of the cylinder is 600 into L divided by density of, it will go in that side and it will get divided, so it will be 900, which gives h is equal to how much? H is equal to 2 by 3 of L. This formula is gone. We have not come to L by D, and there was, in this question there was nowhere written that I should use the formula for metacentric height, but I don't have any other option, since this was the only first formula I should use in case of buoyancy or floating or submergence. But this didn't lead to L by D. It gave me a relation between the depth of submergence of the, okay. So I'll have to, other formula I have is what? Is the metacentric height formula, is the GM formula. GM formula is what? I by volume of liquid displaced minus BG. So this gives me that I have to calculate BG to use this formula, and they have said that this particular cylinder is floating, means my GM is what? My GM is greater than 0. So I can use this condition. First of all, I have to calculate I, V liquid displaced, and BG. So for BG, can I say BG? Okay, distance between this distance is AG minus AB, right? AG minus AB, and AG is what? AG is L by 2. AB is what? AB is H by 2. Okay. L by 2 minus, recently we have calculated H as 2 by 3L, which will give me half into 2 by 3 L. L by 2 minus L by 3. This 2 cancelled. So this will give me L as L by BG as L by 6. So this is done. Now we'll calculate I. We know that I will be, for this diagram it will be this area, this not this area, the moment of inertia of this part. So moment of inertia of this part is generally pi r to the power 4 by 4, but we know D, so I have to convert it into D, which means pi d to the power 4 divided by 64. So this is okay. Then again I'll calculate volume of liquid displaced. So volume of liquid displaced, liquid displaced is what? let me bring this particular diagram outside, then it will be good for us to understand. Let me bring this out. So volume of liquid displaced will be what? My water level was here, so volume of liquid displaced will be the volume of this. So volume of this is volume of this circle into height, which means the volume of this area of this circle into height. So area of this circle is pi d by 4, pi d square by 4 into what? Small h. I know pi d square by 4. H is what? H is 2 by 3. Again, h is 2 by 3 of L. 2 by 3 of L. So if I calculate I by volume of liquid displaced, it will be pi d to the power 4 by 64 divided by pi d square by 4 into 2 by 3 L, which will come out finally to be 3d square by 32 L. Okay, so now this formula I'll again bring it down. So I've already got I by liquid displaced is 3d square by 32L minus bg was what? Bg was L by 6. Now for stable equilibrium, they have said in the question that this particular guy is floating, means it is in a stable equilibrium, nothing is happening to it. So this should be greater than 0, which means Gm should be greater than 0, which means 3d square by 32 should be greater than 0. And now we just have to solve this. 3d square by 32 greater than L by 6. 3 into 6 32L was there. 32L. 3 into 6 by 32 greater than L square by d square. L square by d square less than 18 by 32. And if we do square root, cut it 9 by 16, and if we do square root is square root of 9 by 16, then L by D should be less than 3 by 4, which concludes our answer. This is the answer. Thank you guys for listening. I hope you will practice more questions on metacentric height, because if the paper is tough, then they will ask you the metacentric height questions. Thank you.